Hello, this is the section 2.7 lesson. In this section we're going to introduce a very important theoretical concept called the moment generating function. At first glance its definition looks rather scary, but as we'll see it's not quite as bad as it may seem. So let's start off with the definition of the moment generating function. So let x be a discrete random variable with PMF f and range r. The moment generating function, abbreviated MGF, of x is denoted m of t and is defined to be the expected value of e to the tx. Now let's stop right there for a second. So e, that's just the normal number e, 2.17, so on, or 2.71. And now t is a variable. It's not a random variable. It's just a variable. Don't put too much meaning in that letter t, just a variable, and then x. So what we have here is a function of the random variable x. So by definition of the expected value of a function of a random variable, what we do is we plug each value of x into our function, take it times the associated probability, and add them up. So there we go, e to the tx times f of x, add them up over all x in the range. Okay? And so again, it looks rather scary, but let's do a simple example to illustrate how we can calculate a moment generating function. So consider a random variable x with range 2 and 5, and then here's its PMF. Okay? So a simple discrete random variable with only 2 elements in its range. So its moment generating function is, by definition, this expected value of e to the tx. So that means we plug in each value of x into the function, take it times the associated probability. So plug in the first value 2 for x, take it times the probability of 0.25, and then we plug in 5 for x, take it times the probability of 0.75, and that's it. That's all there is to calculating the moment generating function. Now we still have this variable t left here, and so what we have here is a function of t, meaning I could plug in a number for t, like the number 0 or the number 5 or whatever, and get a number. So this is a function of t. That's why we call it a moment generating function. Now where the term moment generating comes from we won't get into. It's not important for our purposes, but this is a function of t. Okay? So there's how to calculate a moment generating function. Next question is, what can we do with it? Well, this theorem is a proof is well beyond the scope of this book, but this tells us what we can do with it. So it says if x is a random variable and its moment generating function exists for all t in an open interval containing 0, that open interval is kind of a technicality part that we're not going to worry a whole lot about. So then this theorem tells us two things. Number one, the moment generating function uniquely determines the distribution of x. So that means that if I know the moment generating function of a random variable, then I can determine its distribution, meaning I can determine if it has a binomial distribution or a hypergeometric distribution or uniform distribution or something like that. And then the second thing this theorem tells us is two things. Number one, the first derivative of the moment generating function evaluated at 0 is equal to the expected value of x. Now this derivative means the derivative with respect to t. So if I take the derivative and then plug in t equals 0, I get the expected value of x. And then second, it tells us that the second derivative evaluated at 0 is equal to the expected value of x squared. So this second part tells us I can use the moment generating function to find the mean, or the expected value of a random variable. And then that part, along with the second part, I can use to find the variance. Okay? So to kind of summarize this theorem, what can we do with the moment generating function? Well, number one, if we know the moment generating function, we can use the first and second derivatives to find the mean and variance of the variable. And we're going to illustrate that here in our next example. Okay. And then the second use is that if we can show that two random variables have the same moment generating function, then we can conclude that they have the same distribution. Now this moment generating function is extremely important, is an extremely important theoretical tool. It's not the most useful practical tool, but we're going to see it come up in a lot of proofs and theoretical results. Okay. So to illustrate this first use, let's look at this example. So consider a random variable with a binomial distribution, which we defined a couple of sections ago. When we defined a binomial distribution, we said that its PMF was given by this. Remember, n was the number of trials, p is the probability of a success in any one trial, x is the number of successes I'm interested in, and then q we're just letting be a 1 minus p. What we want to do here in this example is, first of all, find the moment generating function, and then second of all, use that moment generating function to find the mean, a formula for the mean and variance of this random variable in terms of these parameters p and q and n. Okay. So first of all, let's find the moment generating function. And to do that, we're going to use the binomial theorem, which we briefly introduced back in chapter 1. Which binomial theorem gives us a way of expanding a binomial expression like this. And so the moment generating function, again, is defined to be this. So we take e to the tx times f of x and add that up over all values of x. Here x goes from 0 to n. And so now we're going to take this expression right here and just rearrange terms. Notice that we put the p and the e to the t together and put that to the power of x. Okay. So now we want to compare this expression here to this expression here. Notice that in the summation we have x goes from 0 to n, whereas k 0 to n. So x and k are basically the same. In the a combination we have n, x, and k, so those match up. Now here we have pe to the t to the x and a to the k. So here the pe to the t, that's the same as a, and then q to the n minus x, b to the n minus x. So p is the same as b. So what we have here is something that looks just like the right hand side of this binomial theorem. So now we can plug stuff into the left hand side and we get this. Here's a, here's b raised to the n power. So right here we have a formula for the moment generating function in terms of my parameters p, q, and n. So every random variable with a binomial distribution is going to have a moment generating function that looks like this. Okay, that's what we've just shown there. Now the second part is we're going to find the derivatives of our moment generating functions and then use that to calculate our mean and variance. So to take the m prime, so this is the derivative with respect to t, and so this is just a simple power rule. We're going to take our power out front, subtract 1 from the power, times the derivative of what's underneath the power. Remember, these are all derivatives with respect to t. Okay. And then we take the second derivative by taking the derivative of this first expression, and this is just a simple Calc 1 problem. Now, third step is we're going to use this moment generating function to find the mean or the expected value. Okay? So as that theorem states, the expected value is the first derivative evaluated as 0. So I go up here, wherever I see t, I replace it with 0. And then I clean it up to get this. And then I remember that that q is 1 minus p, which means that p plus q is equal to 1. And so this is np. So there we got a nice simple formula for the expected value of x in terms of the parameters n and p. So remember, in a binomial distribution, x was the number of successes. So this gives us our expected number of successes, simply n times p. Now our last step here is we're going to find the variance. And to do that, we're going to use this alternate form of the variance, sigma squared, expected value of x squared minus mu squared. In terms of expected, or in the moment generating function, e of x squared is m double primed at 0, and then minus mu squared. So now we just need to plug things in. This first part of this next line, that's our second derivative evaluated at 0. There's mu squared. Clean it up. The details here aren't terribly important. This is just algebra. And what we end up with is this right here, NPQ. So there's a simple, easy to use formula for the variance of a random variable with a binomial distribution in terms of the parameters n, p, and q.